still cooked. Great. Okay, now we're talking. I bought this suspicious looking LED matrix from the internet and I wanted to see if I could make it feel alive. Turns out it was a bit harder than I expected, so I did some troubleshooting for you if you ever decide to make one yourself. Let's go! As you can see here, this is an 8x32 LED matrix, but it's really just 4 8x8 matrices joined together. There's also an in and out direction, which shows how it should be connected. The outside is used for daisy chaining them together. To hook it up to the brain, we'll need some female to female DuPont wires. The first one is the classic Arduino Uno board, a microcontroller which is the most common choice of beginner makers, but it does come without Wi-Fi or Bluetooth capabilities built in. It's also designed to repeat the same program fast as firmware in loop, and you write the code in C++. On the other hand, we have the ESP32, which is a bit more flexible. It's the next step. Also, a microcontroller. It comes with Wi-Fi and Bluetooth capabilities built in, and we also can develop in MicroPython. So we can choose between C++ or MicroPython, which give us more flexibility. But for this project, I decided to use the actual boss, the Raspberry Pi. And it does come with 8 GB of RAM. The crazy thing is there is a version up to 16 GB. Here comes the money, 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 money. So the Raspberry it's different. It's a microprocessor, so it can hold its own operative system and realize different tasks simultaneously. We also have our pinout to connect hardware. And for our purpose, it is more suitable than the other two options. Then I connected the Bluetooth USB dongle to the Raspberry Pi and we are ready to go. We have wireless keyboard and mouse to control our tiny computer. The next thing we are gonna do is connecting our DuPont wires to the LED matrix header. There are some modules in the market that come without the header soldered on, so remember, you always have to weld the headers to the end that says in. Here we have a picture of the connection diagram with the LED matrix and also the Raspberry Pi pinout. It's simple because there are just 5 wires to connect. We will connect VCC to 5 volts, GND to GND, DIN to GPIO 10, CS to GPIO 8, and CLK to GPIO 11. The next step is switch on the Raspberry Pi and start cooking. We'll open a terminal and go to desktop directly by command cd desktop. Then we are gonna create a new directory by mkdir command and the name of our folder. Then we have to go to the directory we just created inside desktop and create a virtual environment, so we can have an isolated workspace with its own dependencies locally, which is safer and more organized. Once our virtual environment is created, we'll have to activate it with the command source vnv/bin/activate, and then we'll be inside of our virtual environment. It's time to install the library that will let us to communicate and send data to our LED matrix. Great, it's time to create our first test script. So, by nano command and the name of our Python script, we will create and open the file. The next step is search for the library docs, and we find out there's a GitHub link. So we go there and we find an examples folder. We will be copying the corresponding test example file and paste it to our just created Python script file. Then I saved it and executed by the command Python and the name of the file. But any sign of life. So I decided to check the hardware, but no, there was nothing wrong with the wire connections. So I moved on to the next thing that could be failing, which is SPI dev. So we have to check if it is active. We have 3 ways to do it. The first one is in the terminal with the command ls/dev/SPI-dev*, and it will tell us our available buses. I noticed there was something weird, and is the SPI dev 10.0, so I thought maybe changing the port in the example test file could work, but I did a fast research and the display should be using the main bus, so SPI dev 1.0 or 0.0, but nothing again. So I decided to check SPI dev in other way. So I went to the interfaces configuration of the Raspberry Pi and SPI was activated. At this point I was so confused and I wasn't figuring out what could be the problem. So I tried to check again in a deeper way and check in the boot config by the terminal if the SPI protocol was switched on. And yes, so what was happening? The thing is that I was sure it was a SPI dev issue, and then I finally found out. The thing is that all the wave behavior was caused because of an old project I made with this system, which was a cyberpunk, in which I had to use a display that also communicated with the Raspberry Pi by SPI protocol. So the SPI dev bus was like trapped by this configuration inside the boot config text file. So I found that DT overlay was causing all the problem, and as you see it was pointing to a TFT display. So the thing that I did is just comment that line and save it. Then I tried again to execute our example script, but again I was having an error. But this time I decided to read it. So the last problem was that the module library for SPI dev communication wasn't installed in our recent created virtual environment. So we just make a pip install SPI dev and we will get this package in our virtual environment. Then I executed the test again and finally, signs of life. We will also have to adjust the orientation and some other settings of the device in our script because some of these displays come inverted. So remember, if you see something strange appearing in the display with the example script but you notice there are some characters, the only thing you have to do is playing with the device settings in the Python script in which you are using the Luma LED matrix library. Now it's time to make it look better. The number of base layers affects how much the LEDs diffuse. You can also adjust the LED brightness to find the sweet spot. And if you want the STL file, just ask in the comments. So now it's time to mount it on the LED matrix and run some first tests with a custom script. I can display real-time data of my actual subscribers by a simple request to the YouTube API. I also can display the actual time, what is the weather and the temperature right now with another request to a free weather API. We can also get the live price of any asset like Bitcoin, Tesla. We also have some cool screensaver modes like this Matrix Rain or the music mode. We could make audio reactive with a simple sound sensor and it would react in real time to the music. We have also this fire mode, which would look so much better if we had more LED matrix connected. Also the Starfield mode, the radar one. So we could make each mode functional and responsive with some sensor modules. and we also could play the punk game just by modifying the script. Like and comment if you would like to see Doom running here. We can also play some games like Snake and control it with a PlayStation controller wirelessly. We can also have a Tamagotchi that reacts to some stuff like what is the weather today or other parameters that you decide, and also use it as a notification or alert device that notice you when a door is opened. For example, we can just connect a buzzer and we will also have sound. What we are doing here is using our Raspberry Pi as a gateway, and each microcontroller or IoT device is acting as a node connecting to our gateway, sending all the real-time data by WebSockets, acting as a web server or any other way. We can also make it notify us when we receive Discord, YouTube, WhatsApp, Facebook, whatever. If you have in mind another use case for this display, if you have a funny or interesting idea, I encourage you to put it in the comments and we will make an update with all the new modes. As you can see, I decided to make a simple UI user interface to make it look better and more intuitive. So this way we can simply manage our different program or modes for the display that we are creating. You could also connect physical buttons or any other sensor and make the display respond with its stimuli. So this way with the UI and the other option with the hardware buttons or other modules are much intuitive to interact with our display than sending commands in the terminal. And finally, we've brought it to life. If you enjoyed this, drop a like and subscribe. I've got a lot of cool stuff and ideas I'd love to share with you. Let me know in the comments if this is something you're into. I'd really appreciate the feedback. See you in the next project.